Welcome to the 8th webinar of the AuScope Geochemistry Network. I'm Alexander Prent, coordinator of the AGN, and before we start, I would like to acknowledge the traditional owners and custodians of the land on which we meet today. In my case, that is the people of the Noongar Nation, and I recognize their continuing connection to the land, waters, and culture, and pay my respects to their elders past, present, and emerging. Now, I'll start off with a short update on the AGN's progress and then go on to introduce the speaker of today's webinar. The goal of the AGN is to create a national collaborative network of geochemistry laboratories. And this is really to help facilitate large-scale national geoscience endeavors, where through the collaboration between multiple laboratories that have similar techniques or the same technique, and them functioning as one, we can really tackle big projects, many data points collected. Now, as you may know, a big part of the AGN's work is to develop AusGeochem, a platform for Australian-produced geochemistry data from around the globe. And this connects laboratories to a repository and provides a service to the geochemistry community. Its development is going really well, and we're currently in beta testing, which means that the code for the software is basically written in stone, so to say. And amongst many things that's possible on the platform, we have the capability to do IGSN minting, which is pretty exciting. More news on that, in the next webinars and also during conferences in the future. Further today, this morning, we received a written confirmation that our collaboration with mindet.org is continuing. And with them, we work on standardization of lithology vocabularies, allowing computers to communicate about rocks in the same way. And lastly, we've been working with CSIRO to develop a laboratory finder, the AGN Lab Finder. And with that, people can find laboratories which help solve the research questions they have in mind. And now to go on for today's speaker, Rohan Glover will talk about new analytical technique that has applications in the geosciences. It's atom trap trace analysis. Rohan has completed his PhD at Griffith University in Queensland in 2012, and since then has gone on to keep working in the similar field at the University of Liège in Belgium, then back at Griffith University for a short while, and now he's really developing a laboratory in the University of Adelaide, where he's a research fellow working on atom trap trace analyses for radiometric dating applications in the geosciences. All right, Rohan, over to you. The screen is yours.
Cool. Thanks, Alex. That's great. Well, thank you everyone for coming along today. It's great to see there's a lot of people in the audience. Thanks, Alex and Brent, for inviting me and organising this. So my name's Glover, postdoctoral research fellow at the University of Adelaide, and I'm working on developing an atom trap trace analysis facility that's located at the Institute for Photonics and Advanced Sensing. So this is a facility for measuring the concentration of the radioactive noble gases. This is for radiometric dating, and there's applications in hydrology and the related research fields. So this is a project which is a collaboration between the University of Adelaide, CSIRO, and Griffith University. Now, what you can see here on the right is a single trapped atom. So this is an image that we've taken with our CCD camera looking at our atom trap. And the way we produce this image is by interrogating that atom with a laser. So it fluoresces, and then we can pick up that fluorescent signal as a single atom. And to measure the concentration of these radioactive noble gases, what we do is take a sequence of images like this one and count when we see an atom. So, is that? There we go. Sorry. Okay, so what that, so we like to count things, and what that looks like is something like this. So this is a time series of data where basically I've taken the integration of an image like the image on the previous slide, and I've plotted that as a function of time, so a sequence of images. Now what you can see is that normally we have this kind of baseline light level. So this is our background signal, and occasionally we get these spikes where there's more light incident on the CCD. So these are when atoms are fluorescing and we're getting a signal. So because in the atom trap we can trap one or multiple atoms, but we can't trap half atoms, it means that these counts are quantized, or the signal level is quantized. So you can see these black dashed lines here, they indicate a threshold level where above that the signal is considered and as an atom, and then we've got several threshold levels, and so when it's above this second level here, there might be 2 atoms in the trap here. So you can see at this point, for example, we've collected 1 atom, and then it stayed in the trap for a little while, and then we've collected a second atom, and then we've lost both of them. So in this way, we can essentially count how many atoms are loaded into our trap as a function of time. So for this 1 minute series of data, that's pretty straightforward. You might have counted 6 or 7 atoms already, depending whether or not we decide to include this small one here. But of course, we normally count for a lot longer than 1 minute, and so a data set might look something like this. And good luck trying to count all of those individual spikes by eye. But you can do it easily with software, of course. And so what you're seeing here is a real data set that we took in the lab only a few weeks ago, actually, and this is a culmination of 5 years of work to get to this point where we can actually measure these things. So really excited to show you this, and it's quite timely that I'm giving this webinar now, just as everything's starting to come together. So this is a signal that's when we count this, it's on the order of 300 counts per hour, and these are krypton-85 atoms, which are incredibly low in natural abundance. So this is a really exciting time for us, I guess. But I guess I should rewind a bit here, because I haven't explained anything about why we're doing this. I mean, sure, it sounds technically challenging and a good result, but what's the purpose? Why are we doing this? And the main reason is because we're interested in better understanding and quantifying our groundwater resources. So groundwater is a critical resource, especially here in Australia. It's the driest inhabited continent on Earth. And so there are millions of people who rely on groundwater for maintaining their way of life. There's massive industry and agriculture that are really relying on these groundwater resources as well. So it's pretty clear that access and management is a really big issue. So this points to things like what I've got listed here, like food and water sustainability, and also understanding and identifying risk to those groundwater systems. So for example, the impact of coal seam gas, which is obviously a hot topic politically at the moment. And then there's also things like understanding the fate and transport of contaminants. So understanding how things like PFAS might move through these groundwater systems, where they would move to, and what's the time scale of that movement. So these are all really big kind of issues, headline grabbing issues, and providing knowledge around this is a geoscience responsibility. So this is a quote directly from the Decadal Plan for Australian Geosciences, and I think it's quite poignant. We as scientists really should be giving the best data and providing the best advice to decision makers around these kinds of things. So how do we actually go about understanding our groundwater? So one of the really important tools at our disposal is things like modelling, and they do a very good job. But you really need to have some hard data as well to put into those models, so that otherwise, I guess you're kind of maybe shooting in the dark a little bit. So you need some data to compare it against. One thing that's grabbing a lot of attention recently is using satellite imagery to monitor groundwater, and that's one approach. Another approach is getting right down into that groundwater and looking at traces. So traces are contained within your groundwater, and by measuring the concentration of them, you can then begin to learn things about that system. So for example, you might be interested in how old that water is, how long it's been there, or the source of that groundwater. So you might be interested in recharge rates and flow rates, and even things like aquifer connectivity. So the plot you can see here, or the graph, shows a number of different techniques or traces that can be used. It's not comprehensive, but it's a good example of what's available. And what you can see at the bottom is the groundwater age in years. So the size of these bars here are an indication of the dating range that each one of these traces is useful over. The colour of the different bars is an indication of what technique you need to use in order to measure them. So ideally, with any groundwater system that you're trying to understand, you just go away and you take as many tracer measurements as possible. And so this is kind of a multi-tracer approach, because each tracer is going to tell you something different. Of course, we don't always have the resources to do that. But my advice is if you've only got a few measurements you can make, or a couple of traces that you can look at, my advice would be to look at the radioactive noble gases. And there are a couple of reasons why. So the first thing is they're a radioactive isotope. So they've got a well understood half-life. You can do radiometric dating, like carbon-14 dating, and so you can get really good temporal information doing this kind of thing. The other reason, which is maybe even more important, I think, is that these are noble gases, so they're chemically inert. And so that means in the groundwater environment, they're not going to be involved in any geochemical reactions. They're really good traces of the physical transport of that groundwater. And this is a really important point, because it means that measurements of these traces are kind of are trustworthy, and they can be used as yardsticks essentially for comparing against the other traces that may be affected by the environment, to then learn more things about that system. So here are the three radioactive noble gases. There's krypton-85, argon-39, and krypton-81. And they cover a span or a dating range from all the way down around 1 year up to 1 million years. So this is covering basically all the age that you would be interested in. There's this gap here where carbon-14 dating is typically used. And the other thing that I want to point out is that argon-39 is a really interesting tracer, because it's the only tracer in this region of in this dating range. So on this timescale of a few hundred years. Now, this is also happens to be the timescale that you'd look at if you were looking at anthropogenic effects on these groundwater systems. So it's an incredibly important tracer in that respect. So you can see that each one of these tracers has a green component over them, so that means you can use atom trap trace analysis to measure it. And Krypton-85 and Argon-39, you can also use radiometry. So, I mean, certainly for Krypton-81, it's clear that atom trap trace analysis, it's the only method that's been proven to be able to be used in a routine way for analysis or measurement of Krypton-81. But what about these other tracers? Why don't I just use a conventional technique like radiometry? And so, next couple of slides, I hope I can convince you why that is. So why use that? So these three glowing balls are representing our radioactive noble gas isotopes, Krypton-85, Argon-39, and Krypton-81, with their relative half-lives. Now, what's really important here is their abundance, and that's what I want to draw your attention to. So for the krypton isotopes, it's on the order of parts per trillion, so it's a very low concentration naturally in these systems, and that means that using conventional techniques, it's actually very challenging. Now, Argon-39 is another 3 orders of magnitude less abundant, so it's even more of a challenge. And so, to give an example of maybe the conventional techniques you might use, so low-level counting is the radiometry technique, and this here is an image of the Krypton-85 low-level counting system that's at CSIRO, and because of the very low concentration and the long half-life, it means that you need to have very large volumes of water and you have to count for a long time in order to make a measurement. And so this is exacerbated even more with Argon-39 because its concentration is orders of magnitude less and it's got a longer half-life. So to do a measurement of Argon-39, you need something like 1,000 litres of water or more, and you need to be counting for on the order of months. So this is by far and away kind of like a routine, simple measurement. And in fact, up until recently, there's only been one lab in the world that does these measurements, and that's located in Switzerland. Just recently, it looks like there's a lab now in the US, which is also using this technique to measure Argon-39. So that's clearly an impediment, though, to some investigations you might imagine. Now you might say, well, what about AMS? That works really well for carbon-14. Why can't we use that? And I guess the reason is because these are noble gases, and in AMS you typically start by creating a negative ion. For the noble gases, this is already quite a challenge. They've got a closed shell, so they don't want to become a negative ion. So you need to have a dedicated facility. You can't go to an existing AMS facility. And there's only really been a handful of measurements done like this. And so it's by far not a routine way of measuring these isotopes, and it's very expensive. And even for Krypton-81, you're still talking about huge volumes of water. So there's certainly scope or space for a different measurement technique. And so this is where atom trap trace analysis comes in. So it's promising that using atom trap trace analysis, we can do measurements on things, something like 40 litres of water for Krypton-85, only 5 litres of water even for Argon-39, and on the order of 100 litres of water for Krypton-81. And I think these, if we compare these numbers to actually what's been done now, because there has been advances, recently, I think the numbers are probably a little bit better these days. So just to put that into kind of perspective, if we're looking at doing an argon-39 measurement using low-level counting, this is what our sample size looks like. It's enormous. It's not very practical. And in comparison, using ATTA, it's something like this. It's something that's much more manageable and is really kind of game-changing in terms of what kind of investigations you can imagine doing. So before I go on to applications, I just thought I'd show how these traces exist in a system and what a measurement is really what you're doing. So the radioactive noble gases are produced cosmogenically, although krypton-85 is produced much more abundantly in nuclear reprocessing plants these days, so it's an anthropogenic tracer. And so these isotopes are existing in the atmosphere and they're absorbed into the water system. So as long as the water is in contact with the atmosphere, so if it's in the atmosphere or if it's on the surface, then the radioactive noble gases will remain at an equilibrium kind of concentration, which is equal to the atmospheric abundance. But if the water is absorbed underground, then this condition is no longer satisfied, and the decay of these traces you can then use that to do radiometric dating. So our clock starts essentially when the water is no longer in contact with the atmosphere. So now this scientist here, he wants to know more about this aquifer. So he does a measurement, he pulls up a sample, and he looks at the radioactive noble gases, and from that he can tell something about the mean residence time of that water and flow rates and recharge rates and these kinds of things. So these are this is essentially the idea behind these traces. So applications, I've already kind of mentioned quite a few of the applications in groundwater in terms of conceptualizing groundwater resources and using them then as inputs for models. And this is really important for sustainable practices and also looking at identifying the risk to these groundwater systems. Now, beyond groundwater, there are also applications. So one example is if you're using krypton-81 to trace very old groundwater and looking at those fluid flows of that very old groundwater, you get an idea of also the elemental mass movement that goes along with that. So this can be used possibly as a way for targeted mineral exploration. So that's a really interesting application. Another thing that you might be interested in is storage of nuclear waste or carbon and hydrogen. And so again, by using krypton-81, you can look at the flow rates around these hydraulically tight rock formations and ensure that there's nothing going on that's going to interfere with that storage facility. Now, the water doesn't have to end up as groundwater. Of course, if you're somewhere where it snows, then the water might end up in a glacier or something like this. So there's also applications in glaciology. One of the really interesting ones is doing independent aging of blue ice outcrops. And likewise, the water might not end up underground, but in the oceans. And the timescale of these large flows in the deep ocean is on the order of hundreds of years. And so argon-39 is an ideal tracer for looking at those processes. So I thought I'd highlight just a few applications that have or a few research papers that have come out recently that are using these tracers just to demonstrate their power. So the first one is a study that was done in the San Joaquin Valley. So this is in California, and it's a region that is very heavily used for agriculture and has been for in the order of 100 years. So I guess it's interesting to ask questions about what is the status or state of that groundwater system, what are the flow rates and recharge rates, and if, for example, I had a contamination at one location, what kind of timescale are we talking about for that contamination to spread? So these guys, they went and they did a bunch of tracer studies, and they looked at tritium and krypton-85, which are young tracers, and they also looked at argon-39 and carbon-14. So the carbon-14 results came back, and they indicated a mean residence time or age of on the order of thousands of years. Okay, so then you look at the other tracers, and they looked at argon-39, and it came back and it said, no, actually, the mean residence time is probably only on the order of a few hundred years. And so now you've got a new question, which is what's going on here, because there's clearly a discrepancy. I guess, like I was indicating, you can trust the argon-39 tracer, and then so we can say what's going on with this carbon-14 measurement. And it turns out that not only using this groundwater for irrigation, this isn't the only impact of this agricultural practice, but they're also using a lot of fertilizers like agricultural lime, and that's infiltrating into the soil, and then from there into the groundwater. And so this is giving you an older than expected age measurement for the carbon. So this is a really good demonstration of how using these mobile gases you can actually find out more information by looking at these other tracers, and this is a good reason why you want to take a multi-tracer approach. It also is a really good demonstration of why argon-39 is a really important tracer, because you can then look at these anthropogenic impact on these systems, and there's no other tracer that's really useful at that time scale. So the next example I highlight is a tracer study using krypton-81, and this was a study done at the deep continental intercalary aquifer, which is in northern Africa, around Tunisia and Algeria. And there had been historical measurements done using chlorine-36 data. But unfortunately, there was really large uncertainties associated with those measurements. So you can see the blue bars here, the large blue bars are the uncertainty associated with these measurements. So clearly you want to do a better job. And so this came out only last year, that they did some krypton-81 measurements, and you can see that's this group of data points here. Now, the uncertainties on them are much better, obviously, but what's really interesting is by doing these measurements, they actually were able to constrain the input function for the chlorine-36 data. So they could go back to these old studies and add value to them with the information that they'd acquired by doing these krypton-81 measurements. So that's a really interesting outcome, I think. The next one is krypton-81 again, and this is looking at groundwater around the waste isolation pilot plant, which is in New Mexico. So here they had flow models looking at the groundwater around this waste isolation plant, and they thought, you know, we need to have some data here to actually back up these flow models. And so the tracer that they chose was Krypton 81 because it's the right kind of timescale. And so doing these measurements, they did a bunch of measurements with Krypton 81, and the tendency was that the Krypton 81 ages were a lot older than they expected. And so they could take this data and they could take it back to their models and constrain those models and do a better job, basically. And the good news was that, you know, actually the flow rates are a lot less than they expected, and so, you know, they're looking at the region around a waste isolation plant. So this is kind of what you want to hear. The last example that I'm going to share with you is this study that was done in the Atlantic Ocean, so in oceanography, and this was using argon 39. Now there were some historical measurements, again, using argon 39, and like I said, you know, to do these measurements in the past, you needed on the order of 1,000 litres of water. So you can see here, these black data points here are the measurements they made in the 80s. And for each one of those data points, they had these 4 250 litre containers, and that was just to make one measurement. So they only made 3 measurements, and they confirmed that the age of the water down here was on the order of 100 or so years. But it's interesting to come back now and do some measurements with, now that we have the atom trap trace analysis technology. So now you can do a measurement, you use a rig like this, and it's got 24 10 litre sample containers, and you can get a whole bunch of data points. Now, they were looking at advection and diffusion, and they'd assumed that they were kind of about the same relative magnitude, but they actually found by fitting to this data set that advection is more than a factor of 2 larger than diffusion, and what this means is, or the implications of this is in terms of something like the carbon uptake of the oceans. So if the water is being pulled down to depth faster than previously expected, then the carbon uptake of the ocean is also going to be increased. So this has kind of broad implications for climatology. And this is all made possible basically because, you know, using atom trap trace analysis, you can do these measurements with a 10 litre sample. It's a really good example of how this is kind of a game-changing technology. So now we get to the nitty-gritty part of the talk. So how does that actually work? So my background, I'm not a geophysicist or a hydrogeologist. My background is in atomic, molecular and optical physics and in atom traps. So atom traps are a tool for confining and cooling atoms. And so this is an image of the rubidium magneto-optical trap, which is at the Institute for Photonics and Advanced Sensing. And you can see here, right in the middle, there's a glowing ball, and this is a rubidium trap. So these are rubidium atoms in the center of this chamber. So they're trapped using laser beams. So there's 3 pairs, so 1 for each dimension. So you've got this set here, this set here, and there's a set that goes straight through. And so by using all of these laser beams, you're able to confine the atoms to the center of the chamber, and you've got long interaction times. And this means that usually these tools are used for doing precision measurements in atomic physics, looking at fundamental physics tests, and investigating quantum mechanics. So this is a long way away from the earth sciences. But they've got another property which makes them interesting, and that's that they're highly isotope selective. So this means that in this particular rubidium trap, you can either choose to trap rubidium-87, for example, or rubidium-85, but it's actually very challenging to trap both at the same time. So I'll try and explain why or how that works. But first of all, I'll just acknowledge that this technique was developed in Argonne National Laboratory by Zentian Liu. So the first paper on this came out in 1999, but it wasn't until about 2014 that it was developed enough that the sciences community started to take interest, I guess. So it's an atom counting technique rather than a decay counting. So you can count atoms, and you're not limited by the fact that you're waiting around for decay events in order to make a measurement. Now, one of the key factors here is that it relies on interacting hundreds of thousands of times with an atom. This is key. It's a really important point. Now, the other thing is that when you've got a different number of neutrons in the nucleus, there's a shift to the atomic energy levels, and this shift means that you need to interact with this atom using a laser. You need to slightly shift the energy or the frequency of that laser so that you can either target argon-40, for example, in this example, or argon-39. So if I tune my laser here, I've got a strong interaction. So the y-axis here is an indication of the strength of the interaction between the atom and the laser. Now, if I tune my laser here, I've got a strong interaction with argon-39 and a weak interaction with argon-40. It's about 4 orders of magnitude less, which is significant, but it's not 16 orders of magnitude, which is the difference in concentrations. So this is where we have to remember that actually we interact with this hundreds of thousands of times. And so the relative sensitivity is something like the ratio of the scattering rates, so something like 10 to the 4 to the power of n. So this is enormous. This is an enormous number, and so this really indicates why this system is so isotope selective and why you don't get any noise from the abundant isotopes. So this is what a system tends to look like. It's something like this schematic here. So you're inputting your sample in this side as a gas. There's a bunch of instrumentation which is all designed to create a high flux atomic beam. Now, this is a neutral atomic beam, not an ion beam. And then these atoms fly down here. They are slowed using a Siemens slower and collected in a detection chamber. And this is where we have our EMCCD, and we look for atoms. And you can see this is a video file of exactly what the EMCCD sees, which is most of the time nothing. It's just kind of noisy, but occasionally, like then, you see an atom, and this is how you do the counting. It's important that you are operating in a single atom regime, because then the measurement is digitized. You're just counting as another atom, and that means that a lot of systematics, which cause small fluctuations, are kind of drop out, and so that's a really important point here. Now, the other thing that's important for ATTA is, that's another atom, is that you need to do sample recirculation in order to get the sample size down to a volume which is giving us these small sample sizes. So this means rather than exhausting a sample directly to atmosphere, we take the exhaust from our turbo pumps and we inject that back into the source chamber, and so this is another critical factor in order to get those sample volumes down. So quickly about the world ATTA capability, there are not many of these systems in the world. There are 3 groups in the world doing radiometric dating, and will be the 4th, but the only one in the Southern Hemisphere. There's another group at Columbia University, which is here, which are doing looking at ATTA for detecting the concentration of krypton in xenon, and this has application in the next generation of dark matter detectors. But if we concentrate just on the radiometric dating groups, there's argon, which is where the system was first developed. In Heidelberg, we're the first to do argon-39. So this is, like I said, this is 3 orders of magnitude lower in abundance. This was quite an achievement, I guess, to get to argon-39. And then there's the group in Hefei, which is in China, and so they've come along with the resources that China has, and they've built a system for each one of these isotopes, and I think they're planning on upscaling this and having more of these systems in place. But you can see at the moment there's a backlog, and if you look at it, there's only really a few hundred samples a year globally that can be analysed, and this is, I guess, it's a really good point as to why we need to develop this system here. So we've kind of got a capability in Australia. I mean, we've seen over the last 2 years that this supply chains can be disrupted. So this is an image of our facility, which is at IPAS. So we got a LEAF grant in 2016, and that's when we started this work. And at the time, though, the work was spread across Adelaide and also Griffith University in Queensland. And so it wasn't until 2019 that we got the lab space that you can see here, and we started building up the facility like you see it here. So we've got our source chamber here, and then our detection chamber down here with the camera, and all of the electronics and laser systems are behind. So I just thought I'd highlight one technical challenge in doing this measurement, and that's that it's actually very difficult to get to the point where you can image a single atom. And the reason is because, as I said, how these atom traps work, you've got all of these laser beams that are being injected into that detection chamber in order to trap the atoms. And so that's on the order of 10 to the 18 photons per second. Now, the fluorescence that you can detect from an atom, you've only got a limited solid angle, is on the order of 10 to the 4 atoms per second. So you only need a little bit of scattered light to reach your camera before your signal is completely swamped. And so that was one of our problems for a while there. We were staring at noise going, is that an atom or not? I don't know. But in the end, we solved that problem, and we just had to listen to more Rolling Stones, it seems, because the answer was just to paint it black. So this is the inside of our detection chamber now. We use a carbon nanotube based black paint, which is highly absorptive. And if you saw a viral video or image that went around a few years ago of this car that was painted like blacker than midnight, we're using a similar kind of paint to that. And so this was key to us for us to get this technology working. But you can see, these are the same results that I showed at the very beginning. Eventually we get to the point where we can image these single atoms, and with our count rate of 294 krypton-85 counts per hour, we can do a comparison with the krypton-83 loading rate. So these are both measurements of an atom per unit time. So we can take the ratio of them to get the krypton-85 concentration. So we measure that to be about 2.7 by 10 to the minus 11. And this is in close agreement with an independent measurement using radiometry. So the next thing that we're really looking to do is to demonstrate measurement of krypton-81. At the moment, with our count rate for krypton-85, that'll be around 5 to 6 krypton-81 atoms per hour. which means, to get any significant statistics, we'll be counting for a long time. So we have some work to do to build up our count rate, but we know this, and just as a comparison, so these other groups are getting a count rate probably around 3 orders of magnitude higher, but they've also been working on this technology for 20 years. So we've got a little bit of catching up to do, but there are some things that are quite obvious that we need to do to improve that, and so it's a good pathway forward, I guess. So the last little bit, I just want to talk about sampling and gas extraction, and for this, I guess we have our collaborators at the CSIRO who are experts on the stable noble gases. And so these are also hydrological traces that are complementary to the radioactive noble gas traces, and I guess possibly a subject of another webinar in the future. But if you're interested in these, get in contact with Axel Suko. And this is an image of their lab where they've got a Helix MC static mass spec, and the system is fully automated, and they can do 400 odd samples a year. And yeah, so they're also experts on sampling and gas extraction of these noble gases. So this is the kind of, this is something we're still working on, because we're only just getting into this space now where we can think about doing measurements on real samples. This is an example of the kind of container they used in that study in oceanography, which is a 20-litre sampling container. You can then take that and you can do gas extraction at the lab. So the guys at CSIRO know all about doing this kind of stuff. They also have a way of doing a gas extraction in the field. But for this technique, you've got to lug around this 50 kilos of equipment. And so one of these two methods will be a good way to extract those gases. I guess that's still something that we need to work out. It may be that in some situations one method works, and in other situations we use the other one. And from there you need to do gas purification to get a pure sample of argon or a pure sample of krypton to take to the ATTA lab. So our target capabilities are kind of 50 to 100 samples a year. This will be a unique facility where we are targeting all 3 of these isotopes. So the other facilities that I highlighted, they have a system that's used for krypton or a system that's used for argon. They're not building one machine to do all of these things. If we had the resources of the Chinese group, we would do that, but we don't. So this is the approach we're taking, and we want to be able to do a measurement of 40 litres of water for a krypton-85 measurement, 39 litres of water for an argon-39 measurement, and 100 litres of water for a krypton-81 measurement. So, and hopefully this is something that we're doing kind of in a semi-commercial fashion in the not too distant future. So to summarise, I hope I've convinced you that these noble gas radioisotopes are really powerful and robust traces to use in hydrology. We should be using them more to better constrain any modelling we're doing and to better understand our groundwater systems. They are extremely challenging to measure, but I guess they're quite simple system compared to some of the other traces, so they're well worth it. And we're developing this facility in Adelaide for doing these measurements. We've demonstrated a measurement on krypton-85, and we expect to be able to do a measurement on krypton-81 very soon. And so I guess now's the time in the talk where I thank everyone who was involved, especially Phil Light, who was involved in putting together the original LEAF proposal and was the leader in the lab for the majority of the time that we've been working. Unfortunately, we lost him to basically an offer he couldn't refuse coming from the commercial sector. So he moved on at the beginning of this year, and so it's been me since then. I'd also like to It's always good to highlight the students that have been involved in these kinds of research projects. And surprisingly, I noticed there's only really one student here, and that's Dash Chetty. So I'd really like to thank him for his contribution as well. And thank you to the audience today. Thank you to all for listening. I hope you found it interesting.
Hey, Rohan, thank you. That was fantastic. Really interesting